Well, hi there, sports fans. Welcome to another exciting edition of Physics 12. And today we're going to start to look at torque. And you've probably come across the term before, but you may not know exactly what it's referring to. You hear the term used quite a lot when you see advertisements for, especially with pickup trucks and the size of their engines and how much torque that they produce. And of course, here's a typical ad of I think this is a Ford diesel engine. They're a Duramax diesel, and they're bragging that it produces 765 pounds-feet of torque, Sonny. And so these are different units than what we actually use, because obviously these are the imperial units, and we will be looking at metric units. But you probably come across this before many times, how much torque an engine produces, and they make comparisons and all that kind of thing. So what do we actually mean by torque? And so torque, to make an object start rotating, which is what torque does to an object, torque will start to make an object rotate. Then a force is needed, and the position and direction of the force matters in terms of how that object is going to rotate. And so the the perpendicular distance from the axis of rotation of the object, so we're looking at axis of rotation, we sometimes call it the pivot point. So the axis of rotation to the line along which the force acts, that's called the lever arm. And so that's quite a mouthful, so what do we mean exactly by that? And here's sort of a diagrammatic representation of that, or an image of that. So if we're looking, this would be the top view of a door. So you're looking down on the top of a door right here. Here's the hinge of the door. There's the doorknob, both sides of the doorknob. And so a torque is produced on the door and it's showing from two different places. From a force here at A, and then another force over here. And so both those forces, they would produce a torque. So let's look at those a little bit more closely. And so here's our door once again, and here's the hinge, which often we refer to as the pivot point, or sometimes referred to as the axis of rotation as well, because we're talking about now moving something in a circular kind of a motion. So again, here's a door, here's our top view of the door. And in this case, the door would open in that direction, shown by the arrow there. And so these two forces here, they would produce a torque on the door in order to open it. And the symbol that we use for torque is the symbol, it's called tau. And this is the symbol that we use for torque, and it looks like this here. So if we want to know what the torque that's produced by a certain force is, then it's just simply the magnitude of the force times its distance from the pivot point. All right, so that's all that torque is. This is the formula for torque. Notice it doesn't. It's not really a vector, but we do have to consider the direction of the torque, which we will talk about in just a minute. So if we look at the torque that's produced from force A over here, and we just put some numbers on there. Let's say this distance is 1 meter, and force A is 10 newtons. Then the torque that it produces would just simply be 10 times 1, which is 10 newton meters. So that's the units that we use for torque. The units are indeed Newton meters. So that's a little bit different than the imperial units of foot-pounds. So we will be using these units right here. It's just simply Newton meters. It's the force in newtons times the distance, which is measured in meters, and so just simply Newton meters. That's all. Now, we also have to consider the direction of the torque that's being produced, and we always go back to the pivot point here. So in this case here, so from the pivot point, this torque is going in this direction here, so that would be counterclockwise. So this would be a counterclockwise torque. Again, as I mentioned, it's not really a vector, but you do have to consider the direction. It's either going to be clockwise that way, or in this case, this torque is producing a counterclockwise direction of a torque. Now, if we look at the other force here, now this force is closer to the pivot point, or the axis of rotation, and let's say that was 0.25 meters. The torque that this produces now is just 2.5 Newton meters in a counterclockwise direction. So this is just illustrating that the further away that the force is applied from the pivot point, then the greater the torque. And that again is given by the formula for torque, which is force times the distance from the pivot point. And so you've probably experienced that yourself, where the longer the lever arm that you have, in other words, the longer the distance from the pivot point, the greater the torque that you can produce. And that's very useful when it comes to using wrenches like this, like a pipe wrench here, or a tire wrench here. Again, the longer the lever arm, the more torque that you can produce for the same magnitude of force. All right, so lever arms at different angles. Unfortunately, your force is not always going to be perpendicular like this one right here. And so we do deal with components, unfortunately. So components are going to show up once again when we deal with torques. So here, with force A, the distance from the knob to the hinge is the lever arm. All right, so because this is perpendicular to the pivot point, then we just simply use this distance right here. However, for force D, what you can see is that force D goes right through the pivot point. That's not going to produce any torque. And if you were to just think about it, if you were to push on the end of a door like this, if the door is open and you just push it on the end of the door like that, it's not going to cause the door to open or close. And so it just simply makes sense that that does not produce, if it's going right through the pivot point, it's not going to produce a torque. It's not going to cause that object to rotate whatsoever. However, if it's on an angle like this, then we need to use the component, or in this case, what we're measuring is the perpendicular distance of the line of force. Okay, so here's our line of force right here, and this is the perpendicular distance right here. Now, we can do this in a couple of different ways, actually. So if here is where our force is being applied, we can either use the perpendicular distance like this, or what we can do is we can actually just use the component of the force that's perpendicular to the hinge point, or the pivot point, I should say. And either way works. In some cases, it's better to use the component of the force. And other examples, it's better to use the perpendicular distance. Now, most of the time, you'll probably be using the perpendicular component of the force. But sometimes you want to use this. And here's an example where the perpendicular distance works better. So these kinds of examples right here. So this would be producing a torque of 700, which is the force produced by the bicep muscle here. And the perpendicular distance that it's acting from the pivot point, or the axis of rotation, is 0.05 meters. And so the torque then is 35 Newton meters. So here's an example where the perpendicular distance is easier to use. Just a couple more things that we need to look at. And here's a case where, let's say you just have an object and its pivot point is down here. And as long as it's of uniform density, then we can consider for it to have its center of mass right here. And that is useful because you can consider all of its mass to be centered at that one point right here, the center of mass. So as long as it has uniform density, you can use the center of mass, which would be right at the center of the object, and you can consider all of its mass to be right at that point there, which is very useful at times. So the last thing that we need to talk about is just net torque, and that's just simply where you look at the sum of the torques in the counterclockwise direction minus the clockwise direction, or it's the sum of the torques in the clockwise direction minus the sum of the torques in the counterclockwise direction, whichever one is larger. So if this one is larger, then you would go this way. If this one is larger, then you would go this way. So in this case, your net torque would be counterclockwise. In this case, your net torque would be clockwise. So the torque, again, is a concept which you've probably come across. You've heard the term before, but you may not have known exactly what it means. And it's just simply the amount of force that's applied to an object which is measured from its axis of rotation, which is the distance that the force is applied from. And it's just a simple equation, force times the distance, and again its units are Newton meters in the metric system.